Today's recitation style videos will be about Newton's laws. We will record several problems when we go through the steps that will help you to solve any problem when you use Newton's second and Newton's third laws. So problem number 1 will be about a block which is on a frictionless surface. There is no friction between the block and the surface. The block is at rest, and there is a force acting on this block. The force has magnitude F naught, and it is at angle theta with horizontal. I will remind us that there is no friction. No friction. Mass of the block is given. F naught, magnitude of the force, is given, and theta is given. What we want to find? We want to find the normal force acting on the block from the table, and we want to find the acceleration of the block as it moves. This is given. And we are looking for normal force. Let me write it. Normal. I will call it N. And we want to find the acceleration of the block that we call A. So what are the steps? First of all, let's figure out which law we will use. Well, you already probably know that we will use Newton's second law. That tells us that net force acting on the object is equal to mass of the object times acceleration of the object, where F on the left is a vector sum of all forces acting on the object. I will break this vector equation into in components. We will work with components when we write Newton's second law. So x component of the force is equal to max, and y component of the net force, again, F sub x and F sub y, are net forces acting on the object. So this is our system of equations. This is our law that we will use. What is the next step? Next step, I need to draw the free body diagram. Free body diagram. Abbreviation, we will write it as FBD, free body diagram, which means that we isolate this block and we draw all forces applied to this block. So here is this block again. What are the forces? All forces acting on the block. There is force of gravity, mg, acting vertically down. There is normal force, force of reaction, acting vertically up. There is force F naught, acting at angle theta naught with horizontal. F naught, I don't put a vector sign. F naught stays for magnitude as well as mg and n, and my arrows show the direction of the force. And I remind ourselves that angle theta is given. Okay, so what is next step? Law, free body diagram. There is no other forces. We draw all of them. Next step is choice of coordinate system. I cannot write projection of net force in the next direction without knowing what is my coordinate system. So natural choice of coordinate system. Choice of coordinate system is arbitrary. It's supposed to help us to solve the problem. So I will choose x to the right and y up, perpendicular to x. Now I'm ready to break all forces in components and write net component in x direction and net component in y direction. So mg is along negative y. It will have just y component. Normal force is along positive y. no x component, only y component, my force F naught will have both components, x and y. And since this is the first problem that we are solving, let's write the components of F naught. So how to do that? As we learned in our previous series of videos, or you knew that before, we try to find right triangle that will work for us. So I will draw the line perpendicular to x, and I realize that this vector F naught is a vector sum of two vectors. This vector and this vector plus this vector. Vector sum of these two vectors. So x component of F naught is positive, and it is F naught cosine theta. Y component of F naught is negative. I put minus, and it is F naught sine theta. Now I'm ready to write Fx max. So what is my net force in x direction? I have x component. I will probably change the color. This looks great. Let's stay with green. So x component will be F naught cosine theta. F naught cosine theta. There is no any other x component of all forces that are drawn here on the free body diagram. So I'm done with F sub x, and this is equal to max. I need to find acceleration, I don't know it. And second equation that I will write is Fy may. What is net force in y direction? Normal force has positive projection with my choice of y. Gravity will come with minus because it is along negative direction of y. It has negative projection in y. And then F naught y also has negative projection. So this is F sub y net force in y direction. And this is equal to may. But the acceleration of the block in y direction is 0, so I'll put 0 here because ay is 0. This is again my system of equations. Now we'll look at it and let's recall what we are looking for. I have two equations, 1 and 2, and I have two unknowns. I don't know normal force and I don't know acceleration ax. So two equations, two unknowns, we can solve it. So from the first equation, I will immediately find x component of acceleration. A sub x is F naught over m cosine theta. And as we just discussed, a y component of acceleration is 0. So we know both components of acceleration. We know the acceleration vector. What is the normal force? We know the direction of normal force. It is always perpendicular to the surface, so it's vertically up. All we need to find is magnitude of normal force. From my second equation, I will immediately see that normal force is equal to mg plus F naught sine theta. So I did not draw it to the scale. If I draw it correctly, my length of normal force vector has to be larger than gravity, because I have gravity plus F naught sine theta. We solved the problem. We found both components of acceleration and normal force.